Hi everyone, this is video 2 of software development from scratch. Last time Tom and Harry built a device to send information. Now they will build another, the one from Charles Petzold's book Code. Tom and Harry are engineers who also trade at the stock exchange. Every day they count their winning trades, their income. Expenses can wait. Each evening they add up the daily trades by hand, column by column, in their journals. They'd already built a device to send information, so why not build one to do the counting too? They knew binary, but only for counting and encoding. How actually do math with it? Add, subtract, multiply, divide, almost nobody know. But one person did. George Boole, an English mathematician and logician, he built an algebra of logic with just two values, true or false. A car is red or not red. Nothing else matters. A signal is there or not. A lamp is on or off. There are Boolean values, and they fit our binary systems perfectly. Well, almost. Tom and Harry studied Boole's work and saw that his algebra could apply to lamps. Time to invent something new. But as always, before you automate a job, you first have to understand exactly what you are automating. Let's recall column addition. Start from the right. 3 plus 1 is 4. 9 plus 1 is 10. But we write one digit per column, so we put down 0 and carry the 1. And we get 204. Now let's do the same in binary. Same rules in binary. Start from the right. 0 plus 1 is 1. The arrow shows the column we're on. Okay, then 0 plus 1 is 1. Then 0 plus 0 is 0. 1 plus 1 is 2, but there is no digit 2. These ones sit in the fourth column, so 4th plus 4th is 8. The next column counts 8s, so we write 0 and carry the 1. Now 1 plus 0 plus 1 we carry it, so it's 1 plus 1 again. Again we write 0 and carry the 1. And 1 plus 0 is 1. There is our results. Let's check it by converting back to decimal. Add up every column that has a 1. First number is 4 plus 8 plus 32, it's 44, okay. Second one plus 4, it's 5. Results 1 plus 16 plus 32, it's 49. And 44 plus 5 is also 49, no mistakes. So now we can add in binary. What else do Tom and Harry need to build their machine? Just one last piece of theory. Remember the relay circuit from last time? To stop drawing batteries everywhere, I'll replace the power source with the symbol V, like this. And now, instead of batteries, we will have this power source here. Now the relay looks like this. It passes the same signal it gets. We will write the signal as 0, no signal, and 1, we have signal. And if we do not have signal on the input, we also do not have signal on the output. In digital circuits, a connection that does one basic logic operation is called a gate. This one is a buffer. It passes the signal through, just stronger. Same idea as our old repeater. Now let's flip the contact. So it's normally closed. The contact goes below the magnet, not above. Each relay still has its own battery, the V's. This one glows all the time, until the switch closes, power the magnet and it's open. This wrong relay flips the signal. In logic circuits, it's a NOT gate. That means it's inverse the signal. If we put nothing, we have the signal. If we put something, we do not have a signal. Voltage in, nothing out. Now connect two relays like this. This is a series connection. No power on either input, nothing at the output. Power one input and it closes one switch, but the second switch is still open, so still nothing out. Same story with the other relay. But turn both at once, and the lamp finally lights up. And let's see, if we do not put anything, we do not have anything. If we put something, only one relay, we also do not have. Only with two signals we have some result. This is the AND gate. You need a signal on the first and the second input to get one out. The keyword is AND. Now connect our two wrongs relays, the normally closed ones, but this time in parallel. Power one input, nothing happens. Power the other, still nothing, but power both, and the lamp goes out. This is the not AND gate. As a table shows, its logic is the exact opposite of AND. We can say not AND or NAND gate. Let's compare the two tables to be sure. Where AND gives a signal, not AND gives none. Makes sense. We can compare this input and output. When AND gives a signal, not AND gives none. So a not AND can be drawn as an AND with an inverter of the output. Easiest than drawing two gates. We have only one diagram. Next, two correct relays in parallel. Power either relay and the lamp's lights. Both on, also lit. So the first or the second or both. This is the OR gate, shown bottom right. Almost done. Now two wrong relays in series. No power on the inputs, the lamp is on. Power either input, it goes off. This is the not OR gate or NOR gate. It can also be drawn as an OR with an inverter. Now, why did we do all this? Remember the binary addition rules. It's like 1 plus 1, 1 plus 0 equals 1. 1 plus 0 equals 1. 0 plus 0 equals 0. 1 plus 1 carry 1. Picture a gate's two inputs as the two numbers and its output as the result. Which gate fits? Or here. OR is closest, but it fails in the last case, because 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, but when we added 1 and 1, we need to have 0, because we need to carry number to the next position. And also, not AND works like that, like we want, like 1 plus 1 is 0, but it does not work here, like 0 plus 0, 1, like 0 plus 1, it's 1. It's wrong here in the first case. Okay, no single gate does that. So we will combine gates to get exactly what we need. Write the gates like this, and we again get two inputs, one output. But now a signal on both inputs gives nothing out, exactly what addition needs. This combination is the exclusive OR gate, or XOR, and it has its own symbol. Yeah, and now we have 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0, 1, and 1 plus 1 is 0, and we can carry another digit. Okay, XOR is the last gate we needed before building the machine that adds binary numbers, the one that will later run your car or your plane. Next we move from the slides to modeling. See you!